You ever just stop and think about the internet? I mean, how do billions of devices all talk to each other without the whole thing just collapsing into absolute chaos? It really feels like it should be magic, right? But it's not. It's all about architecture. So let's pull back the curtain and dive into the invisible logic that keeps our digital world from falling apart, the kind of brilliant and honestly surprisingly simple world of IP subnetting.
So, what's the central problem we're trying to solve here? Well, imagine this. You're trying to deliver a letter in a city with billions of houses, but there are no street names, no house numbers, no zip codes, just chaos. That's pretty much the nightmare the early internet was facing. How in the world do you get a tiny packet of data from your phone all the way to a server halfway across the planet with any kind of precision or speed? The answer, as you might guess, is a really, really clever system of digital addresses.
Okay, so in the beginning, the internet's address system was, well, it was a bit of a digital Wild West. You had this finite number of IP addresses to work with, and the way they were handed out was just incredibly inefficient. I mean, wildly inefficient. And this was creating a massive problem that needed a smart solution, like yesterday.
So, this old system was called classful routing, and its philosophy was basically one size fits all. That was it. It handed out IP addresses in these huge, rigid, fixed blocks. Think about it like this. Imagine a city planner gives every single person the exact same massive plot of land. Doesn't matter if you're building a tiny little garden shed or a giant skyscraper, you get the same mega plot. You can see right away how that's going to lead to some serious, serious waste.
And here's where that one-size-fits-all approach really falls apart. Let's take a super simple connection, just between two routers. We call that a WAN link. It only ever needs two addresses. Period. That's it. But the old system, it would hand over a block of 14 addresses. Meanwhile, you've got a department down the hall with 25 computers that actually needs more addresses, and they also got a block of 14. So you had some parts of the network literally drowning in addresses they could never use, while other parts were completely starving. It was just not working at all.
So, how do you fix this, right? What's the big idea? Well, the first really brilliant solution was something called subnetting. This was the master plan to finally bring some order to all that chaos. If you think of that big, clunky block of addresses as just a sprawling, disorganized city, subnetting is what lets you go in and create smaller, much more manageable, logical neighborhoods.
And at its heart, that's all subnetting really is. It's the process of taking one single large network address and slicing it up into smaller pieces that can be used by lots of different internal networks. You know, it's pretty much the same reason a single zip code can cover hundreds of different streets and thousands of different houses. It's all about creating a hierarchy. It brings order from the top down.
Now, I know what you might be thinking. This sounds like it involves a ton of complicated binary math, and yeah, it can. But here's the pro tip that pretty much changes the whole game. You see, as network engineers figured out, most of the heavy lifting happens in just one of the four number sections of an IP address, what we call the interesting octet. An IP address has four of these number chunks, and once you learn to spot the simple repeating pattern in that one key part, the whole thing just clicks. It becomes way more about pattern recognition than it is about doing complex math in your head.
All right, but we're not done yet. Let's take this to the next level of genius, because this is where it all builds. If subnetting let us create those digital neighborhoods, then the next step, VLSM or variable length subnet masks, that's what allowed network architects to create custom-sized neighborhoods, perfectly tailored to whatever they needed. This right here was the absolute masterstroke of efficiency.
So with VLSM, we can finally go back and fix that ridiculous problem we saw earlier. Remember that WAN link that only needed two addresses? Bam! It gets a tiny mask with exactly two usable addresses. That department with 25 computers, they get a slightly bigger subnet, maybe one that fits 30 computers. No more waste, no more shortages. Every single part of the network gets a custom-fit, perfectly right-sized block of addresses. This is how the modern internet stays so efficient and conserves that precious IP address space. Okay, so you've got all these different custom-sized subnets, which is great, but you could end up with a crazy complicated map, right? Well, there's one final layer of organization that solves that problem, and it's called summarization. The easiest way to think about this is like creating regional maps, a big picture overview that makes navigating all that network traffic way, way simpler.
See, instead of a router having to know about every single tiny street in an entire city, summarization lets it advertise just one simple summary route. It's literally the difference between a highway sign that just says downtown this way versus a sign that tries to list every single street in downtown. It massively cuts down on complexity, it saves a ton of processing power in the routers, and, here's the important part, it's what makes the entire internet feel faster and more responsive for all of us.
Okay, so why do you need to know any of this? Why does all this underlying theory matter? Well, because understanding these rules is the absolute key to fixing things when they inevitably break. The next time your internet goes down, you can bet that the network technician who shows up is using this exact logic to hunt down the problem, step by logical step.
And it usually follows this classic 4-step checklist. First, they'll ping 127.0.0.1. That's a special address called the loopback. It's like asking your computer, hey, can you talk to yourself? It just confirms its own internal networking software is okay. If that works, they ping your actual IP address to check the physical network card. Still good? Okay, next they ping your gateway, that's your router, to see if you can even get out to your local network. And then finally, the big one, they ping a remote server, something like google.com, to see if you can reach the wider internet. It's a beautiful logical process of elimination that isolates the problem one step at a time.
So when you put all these pieces together, you've got the organized neighborhoods from subnetting, the custom-fit efficiency of VLSM, and those big picture maps from summarization. What you get is this incredible, invisible structure. It's this whole system of simple, really elegant rules that takes what could be total digital chaos and transforms it into the seamless, ordered, interconnected world that we all pretty much rely on every single day. And that kind of leaves us with a final thought to chew on. This pattern, this idea of simple, elegant rules creating a massively complex and functional system, that's not unique to the internet, not by a long shot. You see it everywhere. You see it in biology, you see it in economics, you see it in the very structure of language itself. So the question to leave you with is, what other complex systems are all around us running on some hidden, simple, and logical architecture that's just waiting for us to figure it out?